Modeling of ant foraging dynamic using a multi-agent system. The presenter is Maricruz Rangel, and the work were made by collaborators from Puebla, Mexico, and the BUAP University. As an abstract, we have that ant foraging dynamics constitute some of the basis for searching and optimization algorithms in biome-sparse system in the context of computational biology. This is mainly because an anthill is a decentralized system formed by many subunits interacting with each other to give rise emergent collective behaviors. So a decentralized system means that nobody is in charge to make any task. So in this work, a simulation model of ant foraging is developed considering rates of number density changes in the three environmental zones: nest, search area, and food sources located in an artificial anthill. The solution model includes a linear model of differential equations with its analytical and numerical solutions, and additionally a multi-agent methodology. The main result, after performing a comparison of foraging behaviors, is to verify the equivalence between the population dynamics of the different models through a classical entropy parameter. So the introduction have similar information, and we can add that the numerical solution employ a second-order Runge-Kutta method, and also that the multi-agent simulation applied to the anthill collective foraging behavior is based on the agent individual rules. As a result, first we present the mathematical model that was taken from the Kamasin and collaborators in 2001. So in this scheme we can see in the compartment that we were mentioned before, nest, searching, and food. So when an ant leaves the nest to searching food, successful ants find the food and load up before returning home, while unsuccessful ants return directly home. The average rate of ant numerical density changes in each compartment is the inverse of the time spent in each compartment. The ratio number of the ants in every compartment is determined by the solution of the following system of ordinary differential equations. Here we present the meaning of each parameter, for example, the number of ants in the nest, the number of ants searching for food, and the number of ants in the food sources. Also, we present the rate at which ants leave every compartment. Here we present the linear model and the analytical solution. At first, we consider 100 of ants at a time t equal to 0 located in the nest, and here are the standard parameters that are obtained from the foraging experiments. The general solutions graphic are presented, and the stationary differential equation of the system solution are presented in here. Linear model and numeric solution, and according to the second-order Runge-Kutta approximation, the discrete representation of the continuous model is expressed as follows, and the g function are the correspondent of the right-hand side of the equation in the continuous model. A multi-agent simulation model where each ant is an agent, meaning it is a software entity equipped with a set of state variables, for example, the location, step size, direction, perception, and the perception zone are represented in this figure for each ant. Also, the action can be perception, decision, and performance, and by implementing a multi-agent simulation, the interface of the ant foraging dynamics include the graphs corresponding to the analytical and the numerical solution model. Besides, the spatial patterns and the number density is obtained after taking an average of several experiments. So we take a NetLogo applet that already exists in the platform as a basis model, and we made some modification to try to adjust to our comparisons of this modification made is the possibility of the variation of the nest radius, the number of the initial food sources, the possibility of choosing the initial number of ants, the establishment of the time you want to renew the food sources, and also the graphic information to be able to make the comparison with the curves, with the analytical and the numerical results. A comparison of the collective behavior models of the ant foraging at a constant rate or on is described by a classical entropy parameter that is defined like is presented in here. So we can saw this curve that present in red the entropy and in black the theoretical entropy. Some of this conclusion is that the analytical and numerical solution of the linear model of ant foraging are implemented. Also, a multi-agent model of the anthill is extended to include the linear model and variance of the rate of changes and the number of density of foraging ants. And finally, that a classical entropy parameter is proposed for comparison of the self-organization performance in different systems.